for attending my presentation. It's a pleasure to be back here in Hanyang. This is my third time I come here. I have one of your colleagues who is a PhD student with me now from Hanyang. So our relationship has been very useful and productive. And of course, Professor Jun Yang is a graduate of my department also. So I prepared two presentations. I didn't know which one, and then I asked Professor Park. I said, both, why not? So I hope it's useful to you. So the first one, I want to talk a little bit about some of the research that we have, and just give you a flavor. Maybe I'm not going to go deeper into any special topic, but I'm going to give you kind of an overview of what are the direction of research that we are moving on. I think our field of transportation is evolving very quickly. It's changing. There are a lot of new ideas, and really a lot of engineers are working in transportation, even if they are not strictly transportation engineers or civil engineers. We have a lot of electrical engineers, computer scientists, automotive engineers, because there are a lot of opportunities, a lot of ideas, and everybody wants to be involved in transportation. So that's a good time for us as transportation engineers, but also it's a challenging time because we have to understand a lot of new things. So I want to today touch on a few important subtopics such as AI, big data, real-time applications, computer vision applications. I want to talk a little bit about simulation and what we can do, simulation or digital twinning, which is beyond simulation. And also a concept that we came up with at my university, my team, several years ago, the concept of proactive traffic management. You all maybe hear about what's active traffic management, but I want to talk a little bit more about proactive traffic management. So, what did I do? All right. So what we have now is a lot of new data types that we are using. Maybe the first circle has some of the now we can consider traditional data, not very new but still different, which are such as probe vehicles, for example, GPS data, what we call ITS data, such as sensors data, etc., weather data. These are being used more and more in transportation, but I also want to draw your attention to new type of data sources such as videos or images or data coming from smartphones or LiDAR data. You all, of course, use a smartphone. You know that your smartphone has 7 or 8 sensors. Right? You know that, right? So imagine all of us, we are collecting the data that we are using while we are traveling as pedestrians or vehicles. This is huge data that we can use. So I prepared a chart from one of my recent work that has all the data that we are using in my lab. And I'm sure you are using a lot of these data. So there are a lot of traditional type of data on the left side, which are infrastructure, accidents, conflict, violations, geographic data, etc. But look at the right side, you're going to find more of new types of data, such as microwave detection, such as AVI, automatic vehicle identification data, Bluetooth detectors. ATSPM data is a signal operation data that we are getting live also. So every time the signal change, we are getting this indication in my lab automatically. All this data are real time, and we are capturing it in real time in our lab. So we have fiber optics with the Department of Transportation. So all this data is being collected in real time and fed into our lab. We have also been using the transit data. So all the buses, they have GPS. We are getting this data, location data. From GPS, you can determine speed, for example, acceleration. There are also new types of data such as Waze, Letex, Strava, Twitter. You know Twitter, of course. So these are either new apps on the phone or social media type data that we are also using, because social media, if you screen for the data related to transportation, you can get also more information about how people are traveling and thinking, right? So all this data we are capturing. Waze is a connected vehicle data. I'm not sure if you know about it. It's a UK-based company that has an agreement with vehicle companies. And you know that many vehicle companies now track everything in real time. It's sent to the company. So you are driving, for example, a Ford vehicle. Your steering, your braking, your wipers, your light, your acceleration, everything is being sent live to the company. The company assemble all this data and then sell it. Waze buy it and then sell it to us, right? So therefore, this is connected vehicle data, because this is live data of the, it's not really connected vehicles, but it is giving you very close to connected vehicle data. So you can use this in many applications like modeling acceleration, modeling conflicts, modeling behavior. We use it in a lot of applications. So anyway, I'm not going to go over all this data, but now imagine you have all this data in your lab and you're getting stream of this data. What do you do? I mean, so this is very valuable, right? It's very precious. But the challenge is, okay, so what do we do with it? I mean, there are a lot of things that we can do, right? So now AI becomes a very important, because it helps us to either use this data for prediction or processing this data to get items that we need in our research, right? Whatever your research topic is. So we talked about a lot of data sources, and then we can process it. So AI can help us to process the data. And then after we process the data, AI or machine learning or deep learning can help us use these data for prediction, right? So there is a component of using the data to process the data, and machine learning is very important. And there's a component that we use machine learning to predict using this data. So this is an example of how to use machine learning to process data. So this particular example, everything I present here is a study in my lab. So these are real projects that we really use. So this picture shows you the area in Central Florida where I live and where my university is. And all the orange shapes are where the weather systems are. So you get an indication of what is the weather, precipitation, fog, etc. And all the blue dots are the CCTV cameras on the road. Right? So you see that we have a very dense network of CCTV cameras. And what we did is basically, we found that these weather stations are not very useful for us because they are not necessarily close to the road. And the spacing is very wide. So you cannot get continuous coverage. So what we said, okay, we're gonna now use these cameras and process the images or train the model based on these images to identify the visibility, identify the pavement condition. Right? So now once we train this model could be applied in real time, and the camera, which is designed for traffic, is not designed for weather, will detect the image, and the algorithm or the machine learning will tell us what is the weather condition, heavy rain, light rain, and what is the pavement condition, wet or not wet, etc. Now, this information is collected with the help of machine learning and computer vision, but it's very valuable for transportation, right? Because we know that the traffic changes based on the weather condition, and safety also changes based on the weather condition, right? So therefore, now we have free, basically, source of data, right? Because these cameras are there anyway. So this is an example of how we use machine learning for prediction. This is also a project that we're designing a smart corridor, and the smartphone was the main source of our data. And so we collect from the smartphone the position, the accelerometer, the magnetometer, and all the parameters that we collect from the smartphone. And then we process this data to give us the probability of people driving in certain, like turning right, going through, doing a U-turn. So we model using machine learning the speed and the turning movement of vehicles. Now, why turning movement is important in a connected vehicle environment, you need to know that, right? Because if there is a pedestrian crossing or there is a possibility of an accident and the driver is turning with high speed, you need to warn. And this is the connected vehicle concepts, right? So we can use smartphones actually to generate the data that we need for connected vehicles. So this was part of the smart corridor study. So you can see that what we used, I'm going to just talk about the interesting parts, right? So we are using here sound, camera, LiDAR, UWB, Wi-Fi. UWB, now you have it on your smartphone. You have a UWB, but it's not open yet. You know what's UWB? It's a sensor. You know, Apple, when they created this pod so that you can track your bag, for example. So you put it in your luggage, and then with the smartphone, you know where your luggage as you travel, for example, right? So this is a UWB, but it's not open. But you can buy UWB system outside the smartphone. But soon it's going to be open on the smartphone. So we use it to track pedestrians crossing an intersection. So, but the interesting part is that we use sound also. Have you ever thought of using a microphone in traffic to detect events in traffic? So actually we have a paper about this. So there are certain sounds that you can detect with a microphone and machine learning, of course, to determine what's happening. Is it an accident? Is it a braking? Is it a siren from an ambulance? Only using sound. So as you can use cameras in traffic studies, you can even use sound in traffic studies. And police now use this all the time. You know that, right? So we have, for example, microphones in downtown Orlando. And if there is a gunshot, because, you know, America, of course, we use guns a lot, right? So if there is a gunshot, the microphone will detect the sound and will alert the police. So sound is also important. So anyway, so we use this to achieve, you know, the detection, prediction, prevention, etc. And we can achieve all this with these sensors, right? We can influence the signal timing, account of vehicles, what are kind of events you are experiencing on the road, what is the speed. We can visualize what's happening, like this picture, for example, is visualizing where there is a conflict between a bicycle and a vehicle. We can issue warning using infrastructure to pedestrian or infrastructure to vehicle. So the camera is the infrastructure, right? And the camera is detecting a pedestrian or a vehicle and then sending this information. And then share all this type of data for different applications. So I want to talk a little bit about video, because this is one of the things that actually my team has been progressing in very fast. So there are a lot of things that you can achieve with a camera, you know, video processing. You can achieve a lot of things in traffic. And I think I saw something here, right? You're doing something also related to video. So first we need to detect. We need to detect the object, whether it's a pedestrian, a vehicle, a large vehicle, a small vehicle, whatever. And we need to track it. And by tracking it, we get these trajectories. And these trajectories we use in so many applications. I'm going to talk about it. And then you get out of it all this traffic data and more, right? You can get speed, you can get conflicts or near misses, you can get behavior of drivers, you can get behavior of pedestrians, you can get conflicts between pedestrians and drivers. You can get a lot of traffic parameters by processing these videos, which become very useful in our analysis. And then now also when you look at the detection, there are different ways of doing detection. And we are kind of working in that two-stage detection using Google Images. You know that Google you can get a lot of images, right? So you don't only get the Google Earth, but if you go to Google Earth, you can see also images, a lot of images for every road. And these images help you analyze the infrastructure and also the environment of driving on the road itself. Actually, when you put the images together, you get like a video of the roads, all roads, right? So you can, this is a very good source also of data. And the 3D pose detection is also very important in safety studies, because we start to deal with the object not as a box, but as a human. So you see a lot in video recognition, you see these boxes, right? These boxes moving. But actually, that's good to count. But it's not good to determine the near miss between a pedestrian and a vehicle. You need to see where is the arm of the pedestrian. Is the pedestrian crossing the road, pressing the call button, where the pedestrian is looking. So this is important in modeling pedestrian behavior, particularly in safety studies. So you need to do the 3D pose estimation of pedestrians. So this is software that we developed called ARSYS. And ARSYS stands for something that I don't remember, automatic, whatever, conflict something. And basically, we created a very large data set of drone videos that we analyzed, about 1,500 minutes of drone videos at many locations. So all type of locations you can imagine, roundabouts, intersection, interchanges, weaving areas, all the interesting parts of the roadway network. We flew drones and sometimes multiple drones, and then we use these videos to process using our software. So our software is basically, you feed the video, and the software will determine all the statistics as well as safety indicators. So if you're familiar with safety conflicts, what we call PET or TTC, time to collision, these are indicators of safety that we can get from conflict. So if you have the vehicle trajectories, it's kind of, you see where the trajectories come very close. This is a potential accident. Because if you want to wait for accidents and observe an accident, you'll be waiting for a year, right, to see an accident. But you can observe a lot of conflicts. And if we assume that conflicts are related to accidents, you can model safety also. So I think it's probably
Maybe wait.
I need to wait. Yeah, I pressed several times, so I hope it's not going to change.
The 5 is too heavy, so.
Yeah, the 5 is large.
Oh.
Okay, so this is the software basically. So we do a lot of steps in order to use this software. So this one is a really sophisticated software, and we have the ability, when you fly a drone, the drone is moving, right? So you have to stabilize the video, right? Because the drone with the wind sometimes is moving. So this is the first step, and then we have the ability also to stitch videos from many drones so that you have a long segment that you want to start with. And then we obtain the trajectories and all the statistics, and then we use that for data visualization and calculating of the TTC, etc. So it's a very, and then also we have active learning to improve so that the system is improving as it runs more and more. This is some of the locations that we analyzed using videos, and you can see these are all now papers. And I can tell you that the first one is approach to Toll Plaza in Nanjing, China. And the second one is the approach to, I think, a tunnel in Hong Kong. You are familiar with this place? Really? It's your advisor, right? Yeah. So SZ, Tony Z is her advisor, who is a co-author on this paper. And then this is intersection in Florida. And I think this is an intersection also and a bike lane in Florida. And then this is a weaving section in China. I don't know, I think in Chengdu. And these are 3. So in order to cover the whole weaving area, we have to fly 3 drones and then look at the whole video. So these are all conflict analysis that we use using this system that I just mentioned. And then here you can see, for example, the relationship between accidents and the relationship between the trajectories. This is just for illustration, it's not very important. And then here, a sample of the locations that I was telling you about. And by the way, this data, we opened it. So it's online. If you are interested to study any of these locations and get the trajectories, we can provide you these trajectories. So we first used it, tested, etc. Then we opened it for researchers. So far, there are about 100 university research institutes, vehicle companies that are using this data set. So this is a resource available for you. And not only the trajectories, but we also, as you can see, for every location, we created the digital map or the digital file for the location in 3 dimensions. So you can also drive this location in a driving simulation. So not only you can analyze the real trajectories in the real world, but you can do a digital twinning study using the digital maps and even drive the location so that you want to test, say, an improvement or a new system or a connected vehicle or whatever for the same location. This is also we provided in our data. So here are example of the digital map for the locations that I was talking about. So every location you can download the trajectories, you can download the digital map, then you can use it for whatever studies you want to. Another system that we developed is using the roadside cameras, and not only the roadside cameras, but the CCTV cameras. So you know that many of the video systems, you install cameras on the side of the road, and these are usually high resolution specialized cameras. I'm not very interested in that because these are expensive systems. But I'm interested in the CCTV cameras, which the government is already providing for traffic management. How can we use them? Because these are free, right? How can we use them to improve our applications in transportation? So to give you an idea, in Florida, we have 18,000 cameras on the road. So as if you have 18,000 people looking 24/7 on the road. And the machine learning is the brain, right? So you're thinking, you're looking, you can do everything, right? You can capture everything you want, right? So this is where we are heading. So here we are using the roadside cameras or the CCTV cameras. They have problems. I'm not saying they are perfect. They have problems. But anyway, let's not talk about problems. What I want you to notice is look at the bounding box and look how tight the bounding box around the car. Most of the systems, because we evaluated the market, by the way. One of the jobs that DOT asked us, okay, many companies are coming and claiming they have a very good video system. Tell us, who's saying the truth, who's not saying the truth. So we evaluated the whole market. And most of them, you find this big bounding box that is kind of funny around the object. None is as tight as this. So our bounding box is actually not only around the car, but it's also rotating with the car, which is not in the current systems. The other very important, here is the 3-dimension I was talking to you about. Because when you look at safety, you're not interested in the trajectory of the center of the car. Because in the trajectories in all the systems available is the center of the car. The center of the car is good to count how many cars. But if you are looking at 2 cars coming close and having a near miss, you need the edge of the car. So the database I was talking about does not give you only 1 trajectory. It gives you 6 trajectories. The corners of the car and the front and the side of the car. So therefore you can model safety when the front of this car come near the side of this car. You can model this and not the center to the center because it will not be a problem, right? So this is a very important aspect that we are the only ones that did it. All the systems in the market that claim they evaluate safety, they look at the center of the cars. Very wrong, right? Very different, right? So anyway, so this is another software that we developed. And here you can see one of the examples of how we can do more safety evaluation efficiently. So if you are familiar with, if you work with safety and you have a problem, right? So you discovered, there is an intersection that has a lot of accidents, right? And then, you report, to the government, or the government notice that statistics and say, okay, this intersection has a problem because, over the last 3 years, we have been having more than 50 accidents per year, and maybe few people were hurt. Okay, so this is the first step, right? So after 3 to 5 years, you discover there is a problem. You bring a company consultant, and the company do a study and take a lot of money, and then tell the government, okay, now you need to change that, right? So change that, pay us more, and then we have to wait another 2-3 years to look at whether the accidents went down or not, right? This is what's called a before and after study. Very typical in safety, right? But guess what? How many years did you wait, and how many people got hurt before you concluded whether the problem is solved or not? Right? So this is very inefficient. And with a lot of intersections, a lot of drivers, a lot of problems, you cannot keep up. You cannot spend all the money at all the intersections, right? It's impossible. Okay? So here what we are suggesting, we either fly a drone or we look at the CCTV, and using machine learning and computer vision, we determine what is the problem. So fly 2 days, 3 days, 1 week, right? And collect these videos, processing it with our software. And then, for example, here we are showing these red dots are where a lot of bicycles or pedestrians coming very close to the vehicles. There is a problem, right? There is a pedestrian problem, right? It's very clear. And the solution is very easy, right? So in the US, you are allowed to turn right when it's red, unless you prohibit it. So prohibit the right turn of the vehicles, because the right turn of the vehicles come with the pedestrian or the bicycles. So if you prohibit it, you remove this conflict. And then you fly the drone another couple of days, problem is gone. So in 2 weeks, you achieve what we used to do in 5, 6, 7 years. Very low cost, right? So this is an efficient way to do safety evaluation. Another is to use the cameras to help the autonomous cars. So as you can see, the autonomous car on the top, these are all the sensors, right? You see this picture a lot, right? So the autonomous car is moving, all the lidars, cameras covering all this area. You can see all these shapes are basically what the car is seeing around. Okay. How about if this car intends to turn right, and there is a pedestrian now at the corner crossing the road? The car cannot detect that. But the camera on the road, showing all this green area, can see all this green area. So what is the solution is that the camera detects the pedestrian. Using connected vehicles, this information goes to the autonomous car. So the autonomous car knows that there is a pedestrian around the corner, which means autonomous cars by themselves cannot operate in all situations. But we need the help from the infrastructure, and the camera will be that help. Right? So another example here, pedestrian is walking between cars, and this information is detected using the camera. The information is sent to the car. The driver detects the pedestrian and therefore react accordingly. You know who's the pedestrian, John Young, right?
Yeah.
You know who's the driver?
I know.
Okay. These are two of my students. And this is the Tesla. So the Tesla cannot detect the pedestrian because it's between the cars. Some examples of the work that we did for pedestrian modeling using machine learning. So pedestrian at which location we are, is risky for the pedestrians. The camera detects, and not only the camera detect, but now we are starting to predict. So see, I told you the pose estimation, right? So the pedestrian now is not a box. The pedestrian is a human. You can see the human arms pressing the button to cross. The people are waiting where they are looking, all this we model in order to predict what the pedestrian is going to do. Because if the pedestrian is going to violate, this information needs to be sent using P2V, pedestrian to vehicle connection, so that the vehicle knows that there is a pedestrian about to violate before the pedestrian violates, right? So all this we can model. This is some of the models. All of them are machine learning type models. In this particular case, for example, random forest was the most accurate. But I mean, accuracy above 90%, pretty impressive to model pedestrian behavior. Machine learning and video allow you to do that. Okay, I'm going to shift now to simulation a little bit, just to give you a flavor of what we do in simulation. So we have this multi-driving simulation. By the way, we didn't buy this. We built all this software, hardware. We put the hardware together, and we built the software. And we have these three connected simulators. So what does these simulators help us? Help us model a connected vehicle environment. So these three drivers will be operating and connected at the same time. So they are interacting to each other behavior, right? So they are the drivers. But we connected this simulator to number one, Sumo, which is a microscopic traffic simulator. We connected it also to two very important visualization and animation systems. The first using Unity, and we modeled this, and the second using Carla. I'm not sure if you're familiar with Carla, but Carla is a simulator that is built to simulate sensors in a connected and autonomous environment. So you can also simulate the sensors and simulate the connected vehicle type applications. Right? So basically, three drivers are connected to each other. At the same time, the micro simulation is running and generating vehicles that are appearing in their scene, and they are driving scenarios. So remember when I told you about the open data set and the digital maps for the different locations? We can drive them now because we are modeling this using Unity. So of course, there's a lot of connections between the systems, and what I'm not showing here is that all the system is connected to a cave, a room, where we are simulating. It's in a different lab, not my lab, where we're simulating the pedestrian. So the pedestrian is walking in this cave, and the driver here is seeing the pedestrian, say, crossing the road or approaching the vehicle, and the pedestrian is seeing the vehicle in this lab approaching, right? So pedestrian in the loop simulator is also doable with this system. And this helps us to create what's called digital twinning, right? So you are basically representing reality in the digital world, and then you take something from the digital world and then implement it in the real world. So this connection between the digital and the real world is basically the digital twinning that we are talking about. Some animations here to show you Unity platform, Carla platform. Again, the three connected simulators. These are all students in my lab. These are the digital twinning that I was talking to you about. And you can see the digital and the real image. The Google map and our digital map. You can see how refined and accurate the representation. So it's really realistic. And then we are using Sumo to generate the traffic that the driving simulator you are driving in the traffic. And by the way, a side note, we don't use traditional calibration and validation anymore for traffic simulation. So the concept of count the number of vehicles, we are using actually the drone trajectories to calibrate the micro simulation so that it is a vehicle by vehicle calibration and not the number of cars in 15 minutes and all this. It's very accurate calibration of our Sumo model. Some examples to show you all views of the same. So this is what I was telling you about the drone video. The same location in Sumo, the same location in Carla. the same location in a driving view. This is all the same thing, by the way, but in different applications. Can you advance it from your side? Yeah, and this is also just to give you an idea the difference between Unity and Carla, how it looks, the difference between. And then, of course, we use this for many studies. I want to go one back. Right. So this is, for example, studying a non-controlled intersection, and we want to optimize the capacity of this intersection. So you can see, some of the applications we use the simulation I was telling you about. So here, for example, looking at the percentage market penetration of the different types of cars. So you can have human-driven car, you can have only connected car, you can have connected and automated car, and the percentage differ in traffic. So what is the best combination to achieve the best safety and the best capacity for intersection? What is the best merging algorithm, for example? So all these testing, we can easily do it in this system that I'm talking about. And this is from a paper comparing the different. And then finally, I want to talk a little bit about now the data analytics side. We talked about big data, etc. So this is an award-winning system that we developed for prediction of accidents, or prediction of increased potential of accidents in real time. So basically what we are doing is something that in my lab we have been working on for the last 20 years. How can you predict in the next 5+ minutes if there is a high potential of an accident? So how do you do that, right? So we know that we're getting all this data, right, in real time. Now, if this type of data we relate it to historical accidents, we know what is the condition that preceded historical accident. So in the future, this type of algorithm will tell us if in the next 5-10 minutes there is a higher potential of an accident, right? Of course, it's not as simple as that, it's a long story, but just the idea, right? So now, every type of location in our network is different. You cannot model an intersection like a freeway, like a weaving section, like, they are different. So therefore, what's happening here is in the background, there are multiple machine learning algorithms and the data is being fed live to this algorithm. And the algorithm is giving us an indication of the potential of accidents, which is represented in color in front of you, right? So all this is in the background. This is the user will see this map, and this map is updating every minute. Right? So now you can look, of course, the colors represent the degree of risk, right? So, red means there's a problem expected to happen here in 5+ minutes. So anyway, so this system is actually running right now. I mean, this is again an award-winning system, national level, and this is running now in Florida, and we are expanding it, and it's giving you a lot of statistics about the network. And you can zoom at any location, say this red location can give you, now these are the top locations that need attention. And then it can give you, if you zoom at the location and click on it, it's going to give you the different, what's happening at this location, what is the volume, what is the speed, what is the variance in speed. And then, a traffic operation can assess what needs to be done in real time. And also you can click on the camera and see what's happening. You can also get a weather indication. You can also get a suggestion of what is the solution that you need to do now to prevent this accident or reduce its effect after 5-10 minutes, right? So in this particular example, a combination of ramp metering and reducing the speed limit, for example. And then an animation showing you this solution is also provided. Right? Of course, this is all based on years and years of research and simulation, etc. But this is the bottom line. It's bringing everything in a system. So what we are trying to achieve in my lab is that, okay, so in the middle, this is the analytics that I just talked about. All this data, how we use it to predict. But around is all the video stuff that I talked to you about, right? So you can do with videos a lot of things. You can do diagnostics of safety, you can do counting, you can do OD studies, you can do conflicts, you can do pedestrian conflicts, you can do everything, right? So now if you put them together, you have a very comprehensive system that basically can do anything. And again, the key here is AI, deep learning, so machine learning. Right? So just to conclude, I talked to you about proactive measures, proactive safety or proactive mobility, right? Now we have the data and the ability to predict problems, to predict safety problems, to predict bottlenecks, queues, weather. We can predict everything. And therefore we can adjust so that we don't reach a very bad situation, right? This is what I mean by proactive, improving, whether we are improving safety or mobility. And then now with connected vehicles, we have this continuous connection, right? So we have, excellent data, excellent models, excellent computing capabilities. We can test everything in the simulation I talked to you about. And therefore we have, I think, a lot of opportunities. Yes, we have a lot of challenges as transportation professionals, but we have a lot of opportunities. And then I wanted just to finish with the Future City Initiative, because we had this discussion. So Hanyang is doing this smart city center and concept. We also, around the same time, we had the same thing, but we called the Future City Initiative. So from a research point of view, from an education, we have masters now in smart cities. And I think our masters is the first in the US in engineering smart cities. So we are thinking kind of similar. So this is my lab, UCF Smart and Safe Transportation under the University of Central Florida. So I thank you for your attention. I hope you benefited.
If you want to second presentation, you can continue.
Yeah, less than 10 minutes. So how long did I?
30 minutes.
30? Okay, so you are tired, right? So just I'll talk about maybe 7 minutes. Short presentation just to give you an idea, and then let's go to the second. All right, so this is a very recent effort that I'd like to share with you, because this data, we are going to open it also for your use, everybody's use. Right? So if you're interested, let me know, by the way, and I can leave with the links for the paper that explains the data, as well as for the data where you can download them. So basically we created, and this is the link to the data, by the way, but of course you cannot type it. Anyway, you can take a picture, but it's in your All right, I'm not publicizing this yet because this is very recent and we are still analyzing the data. But basically what we did is that we created AV crashes data set. So you know that most countries, or all countries except the US, did not publish the crash data or the crash reports. So you know that this number of crashes happen, you see it on the news, but you cannot, as an analyst or a traffic engineer, you cannot put your hand on the data. But except California, Department of Motor Vehicles have opened their data. You can request it. And the National Highway Traffic Safety Administration, which is a federal administration, have also, you can get their data. Right? But this is going to be limited to the US. So these are basically what I'm showing you. All these dots are accidents, crashes, AV. Okay, but we split it into two parts: ADAS, Advanced Driver Assistance Systems, which is level 2, SAE level 2 automation, and it's shown in the red color, and in the blue color ADS, which is level 3 to 5. Okay. Both California and the NHTSA has both in their database. Now, when we searched more, we found that news report a lot of autonomous vehicle data in other countries. And so we started to look for news. And the news either good description, sometimes good description and a video, because all these vehicles have a camera. So you can also get the video of the accident, right? So all the other countries that you see here, China, Europe, you have a little, one in South America, a couple in Australia. Anyway, this is all the news that we found, 52 AV crashes. So basically, we put all this and we created a database of ADS and ADAS from the 3 sources, 2 American sources and 1 news, so that we cover other countries. And these are the statistics of the number of accidents on the right side. Okay, so basically here is the NHTSA data, California DMV data, news and social media data. Again, social media to get the public sentiment. And then we use Google Maps in order to identify the location. We use Open Weather API to identify the weather. All this we combine and we created this avoid, what we call avoid database. By the way, I didn't mention at the bottom here, these are the crashes by year that we found. And this is a little bit complicated chart, but it shows you basically the percent in clear weather, the percent of location, the percent of injury. You can see also the percent of rear, right, front is where the autonomous car has been hit in this accident. Hit from the rear, hit from the side. So it gives you kind of a distribution of, and you can see differences between ADAS and ADS. Then we did the interesting part that you all hear about recently, ChatGPT, right? Okay. Is there something that we can do with ChatGPT? We use ChatGPT, right? Because basically, particularly the news part, it's a written article, right? So therefore, we can process it and ask questions to ChatGPT to identify to us, based on the written, what is the reasoning for the crash, what's the attributes, what's the location, what's the type of the crash. Here, for example, is a crash from Germany. Germany do not open the data set, but we found the news from Germany. So now you can process the news article, the social media related to the news article, and then you can extract here the important information. And here we are using ChatGPT basically, or a large language model to, now one of the advantages is that ChatGPT can talk any language. Right? So whether the crash is in Germany or the crash is wherever in China, no problem. It's all, we can get the information. But us as a researcher, without that, we don't know, right? We don't know all the languages. So anyway, so here, for example, you can see this is a crash from China with the video. So now we can even analyze it. Remember, I talked to you about analyzing videos, right? So that now the video can tell us not only the traditional elements, which is weather, severity, etc., but it can tell us what is the speed, was there acceleration or deceleration, what was the maneuver before the crash, what's the angle, the surrounding vehicle. So it can actually, the video can give you even more information about the crash to help us analyze AV crashes. Right? So this is another, you can see the trajectory before the crash. We can, as I said, we can get the location also, and then identify other parameters related to the location. And also we have created this, the video processing feed into ChatGPT, and then we request from ChatGPT to write us like a proper crash report or a report about what happened, right? So it's really, we found it really useful, by the way. We wrote a paper already about that, but still under processing. It was fun, like, me and my students were having fun, doing this type of work. And then here is some general descriptive statistics. So you can see here the crash time, the number of crashes, as I mentioned. The shuttles are the slow-moving ones, the one that you see them, probably you have them in Korea. We have them on campus. But this little bus with 10 people moving slowly. Right? So we have 6 of these crashes. And then we have 870 ADAS, 633 ABS. The years, but really the data was open starting mostly 2021. That's why more. You can see here the operation, what type of operation, and this sample, 70% was the system disengaged when the crash happened. You can see the road type. So for example, here we can see that ADAS happened more in parking lots and highways, while ADS happened more on street and intersections. So therefore, there is some differences within the 2 samples. Lighting condition, the speed, when the crash happened, what was the speed? Then here, you know, I don't want to talk about it. This is like, okay, so now how complicated and do a model. So this is like a injury severity model. And we found actually a few very interesting non-traditional factors when we analyze regular crash data. You know, things about the weather condition, about hitting a fixed object that was different than the regular knowledge that we have about crashes. So these are some, you know, some of the models. All right, so this is the paper that we wrote. It's still under review, so it's in AR-CIF. Here is the URL if you are interested to read this paper. Actually, this paper, I think we put it also at ResearchGate. This is the #1 viewed paper in the last month or so. So people are really interested in that. If you want to read the paper, if you want to look at the data set, just when you use our data set, cite our paper. This is the only condition. All right. That's it. I just wanted to show this for fun. Thank you very much.